recording. Open the notes. Okay. Well, hello everyone. My name is Peyton Boniface, and I'm going to be doing Transport 2, the homework 2. So today we're going to start out with a 10 centimeter long uniform cross-section capillary containing pure liquid on the left side and pure deuterated water, as I'm going to refer to as D2O for the rest of this because I hate saying deuterated. Anyway, we have liquid H2O on the left side and liquid or D2O on the other side, and they both take up 5 centimeters of this 10 centimeter capillary. The other given information we have for this problem is that at t is equal to 0.1 seconds, the maximum molar diffusion flux is 2.78 moles per square meter per second. And we also know that the molecular weight of D2O is 20 grams per mole, and its density is 1,110 kilograms per cubic meter. So moving on to what we need to be solving, we are asked, the first question we are asked is, what is the overall mass flux, or N, corresponding to this maximum molar diffusion flux? So mass flux is described as letter N, and it from equation 1-14 in our book, we know that the mass flux N is equal to the mass concentration, rho, times the mass average velocity. Again, that's equation 1-14. So in order to find this overall mass flux N, we need to start with the first step, which is to find rho, or the total mass concentration. So the total mass concentration is equal to the sum of the partial mass concentrations of, in this case, the binary compounds of water and D2O. So the total mass concentration is equal to the mass concentration of water plus the mass concentration of D2O. And the mass concentration of a particular component I is equal to its mass over the total volume, or the density times the volume of the specific component over the total volume, which is, if I can draw this equation right there. Okay, so moving on, the total volume is equal to the sum of the volumes of water and D2O, and we know that since if we go back up here, they both take up half of the entire container, 5 centimeters each at the same uniform cross-sectional area. We know that the volume of water is equal to the volume of D2O, and that they're both half of the total volume. I refer to as the total volume as just V here. There are a lot of V's in this problem, so it can get a little bit confusing, but if you see just a V, that is total volume. So moving on to each individual mass concentrations, the mass concentration of water is equal to its mass, or 1,000 kilograms per cubic meter, times, and then we are substituting in half the total volume here over the total volume V. So the total volumes cancel out, and you have that half of 1,000, or half of the mass, is equal to the mass concentration of water, which is 500 kilograms per cubic meter, and we can do the same for D2O. However, its mass is just a little bit. Its mass is just a little bit bigger at 1,110 kilograms per cubic meter. Again, the total volumes cancel out, and you're left with 555 kilograms per cubic meter. And then in order to find the total mass concentration, which is step 1, and will help us on our way to solve this equation right here, is the mass concentration of water plus the mass concentration of D2O, which is 1,055. I can't say numbers today. Kilograms per cubic meter. Alright, so moving on to step 2, now that we know the total mass concentration, we need to find the mass average velocity in order to find the mass flux. The total mass flux. So this second step says we need to find the mass average velocity, And what do we know? We know that the sum of Molar diffusive fluxes are equal to 0, because as water diffuses one way, the D2O will diffuse in the opposite way at the same speed in order to fill the space that the water has left. So if the molar diffusive flux of water is 2.78 moles per square meters per second, then the molar diffusive flux of D2O is the opposite and equal in magnitude, negative 2.78 moles per square meters per second. And then we need to find, in order to calculate mass average velocity, we need the individual velocities of these components. So we know that the molar diffusive flux of a component I is equal to its concentration times the velocity of that individual component I. We also know that the concentration of I is equal to the number of moles of that component over the total volume, and that we can break that down even further into things that we know, in saying that the moles of a component I is equal to its mass over its molecular weight. And now we can substitute the concentration in there and moles in there to come up with this equation right here, which tells us that the molar diffusive flux of a component I is equal to its mass over its molecular weight over the total volume times the velocity of that individual component I. And you might think, how does this help us? Well, if we look at this equation, we know the molar diffusive fluxes of these components right here and right here. That drawing was horrible. Right here. I'm going to have to start erasing things. Okay, I'll keep that. We know that the molar diffusive flux of a component I is equal to its mass over its molecular weight over the total volume times the velocity of that. Well, we want to know this individual velocity, so it helps us find the mass average velocity later. So, setting up this equation right here, we know that the mass of the water is equal to its weight times half the total volume over its molecular weight of 0.018 kilograms per mole over the total volume, and then multiply that by the velocity of water is equal to its molar diffusive flux, which is equal to that 2.78 moles per square meters per second. So if we turn around this equation and solve for divide by all this, divide 2.78 by all that, we will get the velocity of water, which is 1.0008 times 10 to the negative fourth meters per second. Likewise, we can do the same with D2O, except again changing its molecular weight and its density, its mass, not density, or excuse me, yes, its density. Its density divided by its molecular weight, again, slightly different than water's, but still different, is equal to that molar diffusive flux of D2O, which is the opposite of water's. Equal in magnitude, though, is negative 2.78 moles per square meters per second. And then if we solve for the individual velocity of D2O, we get negative 1.0008 times 10 to the negative fourth meters per second. So the density and molecular weight did not make that much of a difference looking overall, as they ended up being the same, just opposite, but still same in magnitude. So now we go to the definition of, now that we know the individual velocities, we can go to the definition of mass average velocity, which is the mass fraction of the sums of the mass fraction of the components times the velocities of those components. So in this case, just the binary system, we have the mass fraction of water times the velocity of water plus the mass fraction of D2O times the velocity of D2O. And again, the mass fraction is simply the mass concentration over the mass concentration of the component over the total mass concentration. So subbing that in since we don't know mass concentration, but we can calculate that because we do know we don't know the mass fraction, excuse me, I think I had that backwards. We don't know the mass fraction, but we can calculate it using the mass concentrations. So the mass concentration of water over the total mass concentration times the velocity of water plus the mass concentration of D2O over the total mass concentration times the velocity of D2O gives us the mass average velocity. So we're plugging these numbers in that we already know, 500 kilograms per cubic meter over the total, which is 1055, times those numbers we just found out for individual velocities of 1.0008 times 10 to the negative fourth meters per second. And I ran out of room here, but you can see it's the negative of this number right here. And then after you solve that, you get the mass average velocity of negative 5.27 times 10 to the negative sixth, and that's in meters per second. So the third and final step would be to solve that equation for n, or total mass flux. And if you remember, total mass flux is equal to the mass concentration total times the mass average velocity. I don't know if I'm saying this right. There's too many masses. If I didn't say it right, n is the total mass flux is equal to the mass concentration. I think I said that right, times the mass average velocity. Yeah, okay. And so we plug those numbers in, and we get that the total mass flux n is equal to negative 5.56 times 10 to the negative third kilograms per meter squared second. Of course, this is a mass flux, so it should be, in terms of units, it should be the amount of kilograms going through a defined area, a cross-sectional area, per given time, so that looks right. Moving on to the second question, we have make an order of magnitude estimate for the max driving force for the diffusion at a time is equal, at the time 0.1 seconds. We know that the driving force is equal to the gradient of mass fractions, which is equal to the sum of the mass fraction of the component I times the molar diffusive flux of J, minus the mass fraction J times the molar diffusive flux of I over the concentration times the Stefan-Maxwell coefficient from I to J. How does this help us exactly? Well, we know that the sums of the molar diffusive fluxes have to add up to 0, so we know that molar diffusive flux plus molar diffusive flux of 1 plus molar diffusive flux of 2 is equal to 0 in a binary system, and that we know that the molar diffusive flux of 1 is equal to the negative molar diffusive flux of 2, and vice versa. So expanding upon this summation, we know that the mass fraction, I'm mixing my words up now, the driving force, which is equal to the mass fraction gradient, is equal to mass fraction of 1 times the molar diffusive flux of 1 minus mass fraction of 1 molar diffusive flux of 1 over the concentration times the Stefan-Maxwell from 1 to 1, which simply goes to 0 because there's no difference there, plus the mass fraction of 1, which is, this is the part that actually matters, considering it doesn't go to 1, but the mass fraction of 1 times the molar diffusive flux of 2 minus the mass fraction of 2 times the molar diffusive flux of 1 over the concentration times the Stefan-Maxwell coefficient from 1 to 2. So for binary systems, we also know that the mass fractions of all the components equal 1, and therefore we know that the mass fraction of 1 plus the mass fraction of 2 is equal to 1, and the mass fraction of 2 is equal to 1 minus the mass fraction of 1. And for ideal systems, which we are assuming this is, the Stefan-Maxwell coefficient from I to j is equal to the fixed diffusivity coefficient, or just diffusive coefficient from I to j. So we're placing these variables into the equation. We're replacing molar diffusive flux of 2 for the negative molar diffusive flux of 1, and we're using this relationship here that that's a horrible arrow, but there and there, we're substituting those in as well as this, I guess. Put that, it goes down on the bottom. It's kind of covering things, I'll erase that. So we get the driving force is equal to the mass fraction of 1 times the negative molar diffusive flux of 1 minus 1 minus the mass fraction of 1 times the molar diffusive flux of 1 over the concentration times the Stefan-Maxwell coefficient from 1 to 2. And if we do some algebraic manipulation of the equation here, distribute the molar diffusive flux of 1, we get that the negative mass fraction of 1 times the molar diffusive flux of 1 minus the molar diffusive flux of 1 plus the molar diffusive flux of 1 times the mass fraction of 1, mouthful, over the concentration of the fixed diffusivity coefficient of from 1 to 2. So looking at this equation, this cancels out with that, and you're left with the driving force is equal to the negative molar diffusive flux of 1 over the concentration times the fixed diffusivity, that was an accident, from 1 to 2 is equal to the negative is equal to the driving force. So if we plug in the numbers here, we know that the molar diffusive flux of 1, in this case that's the molar diffusive flux of water, is equal to 2.78, but the negative is still there, so we have negative 2.78 moles per square meter per second over the concentration of water, which is 55,555 moles per liter, times the fixed diffusivity for liquids is 10 to the negative 9th. So that gives us the driving force of negative 5.004 times 10 to the 4th, and our answer, which would be the estimate, an order of magnitude estimate for the max driving force for diffusion, would be 10 to the 4th. So moving on to the graphs, we have, starting with the mass concentrations, we have the mass concentration of water in general is in dashed lines, and D2O is in the thick lines, or the straight, or I don't even know, the regular lines, I guess. So starting off with the initial mass concentrations, we have water at 1,000 kilograms per meter squared, and that's steady until it gets to 5 centimeters, which is where the two meet face to face, and then it drops to 0. And it's the same for D2O, except in the opposite direction. D2O is slightly heavier, so its mass concentration is a bit higher here, but it comes in, and at 5 centimeters it drops to 0. So looking at a time is equal to 60 seconds, we have the water is given more time now, so you can see that after it's beginning to diffuse and the mass concentration is slowly getting across to the right side of that closed capillary, as well as the opposite for D2O, starts off and is given some time, it starts diffusing. And then finally, at time is equal to infinity, you have both of them have stopped diffusing, so you have constant mass concentration across the capillary at all positions, and you have 500 mass concentration for the water, and was it 550, I believe? Sounds right. 550, I believe, was, if we can go back up here, take a look. I'm losing my mind. 555 cubic or kilograms per meter squared for the D2O. Moving on to the molar concentration graphs. The molar concentrations are the same here because the mass does not matter anymore. This is simply moles per liter. So they are the same. D2O is not higher, but this is around 55,555 moles per liter, and then at time is equal to 0.1 seconds. It's similar to the mass concentration graphs in water. Starts off at the same molar concentration all the way up into the place where they meet in the middle, and then drops to 0. And similarly for the D2O, on the right side it's fully concentrated and then drops to 0, and so there's no concentration of D2O on the left side, initially, just like there's no concentration of water on the right side initially in this capillary. And then again, after about 60 seconds, these are given time to diffuse, and you can start seeing some concentration of D2O make it over to the left side, as well as some concentration of water make it over to the right side. And then given t infinity seconds, these will both level out at the same place. Again, like I said, molar concentration doesn't take mass into effect here, so they will be identical, and I did that with the dashed and regular line, so they'll be the same and they'll be constant. Moving on to the molar diffusive flux. The molar diffusive fluxes of the max molar diffusive fluxes are 2.78 and negative 2.78 moles per meter squared second. So at t is equal to the initial state, t is equal to 0.1 seconds, we have water at the initial position. There's no molar diffusive flux, and it spikes really high towards the middle, as it hasn't had much time to diffuse yet, so the spike is really tall, but it does hit the 2.78 moles per meter squared per second, and then goes back to 0. And the same for D2O, except opposite. It will have no molar diffusive flux at the positions close to the wall, and then at the place where they meet in the middle at 5 centimeters, it spikes to negative 2.78 moles per meter squared per second, which just means it's going to the left, since the right is in the positive direction. After about 60 seconds, this graph looks like it's just been stretched out, as it's given more time to diffuse. There's still a little diffusion at the two ends. However, towards the middle, you can start to see that instead of the strong spike, there is diffusion starting to happen near the middles, or near the sides of the capillary, instead of just in the middle. And then at time is equal to infinity seconds, all diffusion has stopped, and the two binary mixtures are completely mixed, and this looks identical to the molar concentration graph at t is equal to infinity seconds. And then finishing up with the mass diffusion flux graphs, we have that both components are, they start at 0, and for the initial graph of time is equal to 0.1 seconds, we have that the mass diffusion flux goes down to the negative 5.56 times 10 to the negative third, and that's in kilograms per meter squared per second. It takes a sharp decline again, like I said, because it hasn't been given much time to diffuse, and most of that mass diffusion is going to happen in right where they meet at the interface of 5 centimeters. And then at the intermediate graph, we have again, it's just been looked like it's been pulled out because it's given more time to diffuse, and you will see that the diffusion is happening closer to the positions of like 2 centimeters from the left wall all the way to like 8 centimeters from the left wall. It's happening here now, whereas it wasn't here and here. And then when you get to time is equal to infinity seconds, there's no more mass diffusive flux, because like the molar diffusive flux, the two mixtures are completely uniform throughout the capillary, and the mass diffusive flux will be 0 because it's constant, not because it's constant, but it's constantly at 0 because nothing else is diffusing anymore after they are uniformly mixed throughout. So if I can zoom out. Okay, so this is what my graphs look like, and that is all I have for you today. So thanks for watching. I'll stop.